Alrighty. So I would love to talk to you all about domain and range, and a little bit of notation, so looking at interval notation and set builder notation, and looking at some variation functions. So if you're feeling super solid about these things, you know, you can skim through this or you could just not watch it, but at least you have this as a resource if you want to go over a few of the things that we've explored and talked about so far. So let's talk about notation first. So notation, this is just really about communicating your thinking clearly, and so we have some standard notation. The two types of notation that we use the most are set builder. Sometimes I write this just as an inequality because it's faster, and it's fine if you want to do that as well. And then interval. So I like interval notation a lot because it's very efficient. It doesn't take very many strokes, and I think mathematicians are either lazy or they like efficiency. So I think that interval notation is kind of nice. But it has some drawbacks as well. Set builder and inequality notation give us more information. So these ones have the curly brackets, and then you can write x such that, you know, -2 is less than or equal to x is less than or equal to 5, for instance. And that would say, first of all, we know we're dealing with domain, right? Because we're using x values. And it tells us that we want all of the x values between -2 and 5, including the endpoints. Another example would be y such that y is greater than 10. Okay, so y is greater than 10 just means, first of all, we're dealing with range because we've got the y values, right? And that's what range is. But secondly, that we want all of the values bigger than 10, not including 10. Now here's an incorrect way to write that. 10 is less than y is less than infinity. The reason we don't need less than infinity is because every number is less than infinity. So it's sort of redundant to write, you know, less than infinity, so we just don't write that. You could write 10 is less than y. That's the same thing as y is greater than 10. This is just a little bit nicer way to write it, I think. Personally, that's sort of my own preference. But normally, I think you'll see the variable coming first. Y is bigger than 10 is the same thing as saying 10 is smaller than y, right? You are taller than your sibling is the same as saying your sibling is shorter than you. Just depends on where you start the comparison. Okay. So there might be one other thing we want to look at with set builder, and that's what if it's all real numbers? So the best way to write it with all real numbers is to write something like x such that x is an element of the real numbers. That's the fanciest way to write it. Again, this is x is an element of the reals. But you can also just write all reals. That's fine. You can just write the capital R with an extra line. Here you could also just write y is greater than 10. Here you could also just write -2 is less than or equal to x, which is less than or equal to 5. So it's okay if you don't put all the fancy brackets. You can just write things like this. You could also just write all real numbers. So I'm trying to get you to be familiar with a few different notations and different ways to write things, and then you can kind of choose what works for you. And then if other people write it in this way, then you have a sense for what they're writing. Now, interval notation uses brackets and parentheses. And it basically gives you your start number and your end, and that's it. So here we would use brackets because it's less than or equal to things. And so we would write this as bracket -2, 5, bracket. Okay? Does not tell us that it's domain, so we have to know that it's domain because there's no x in here. Here we would say, well, what's the smallest number? Greater than 10. 10 is our smallest number, and we can go anything bigger than that, so we go all the way up to infinity. So we write that as 10, infinity. You never put a bracket with infinity because you can't get there. And here, for all real numbers, we simply write negative infinity to infinity. Okay? So these are some ways to write different notation here. I'll just show you that if this were, say, just less than 5, then instead of a bracket, we would have a parenthesis. Okay? So that talks about some notation. I'm going to check the time because I don't want this video to be too long. Okay, we're at 5 minutes, so that seems fine. We've talked about some notation. So let's look at some variation functions and think about their domains and ranges. So first of all, you've got y equals kx. So if k is positive, it looks like this. And if k is negative, it looks like this. Okay. Then you have y equals k times x squared. And if k is positive, it looks like this. And if k is negative, it looks like this. So an example here would be, say, y equals negative 2x squared. And an example here would be y equals 2x squared. So if it's positive 2x squared, it's going to open up. Negative 2x squared, it's going to open down. Here, we might say y equals negative 1x. And here, we might say y equals positive 1x. Okay? These are the direct variation graphs. And we'll look at some practical applications of these next week. Direct variation up here. And then you've got the inverse variation functions. So you've got this one. They've got two different branches. So this one is y equals k over x. And this is y equals k over x squared. And in both of these cases, I've drawn the functions where k is positive. And I'm not going to draw the ones where they're negative because it just gets confusing. Well, I'll draw it and then I'll erase it. So this would be the one if it's negative, it would be there. And if it's negative, it would be here. But I'm going to erase those because I just don't want us to get confused between the different shape of these two. Okay, so this is if k is positive. And we might call this, say, y equals 3 over x squared. Or this might be y equals 1 over x. These are examples of what these graphs look like. Okay, so good to have that basic shape. So when I'm thinking about this, I know that kx is just a line. I know that kx squared is a parabola. I know that k over x squared is a volcano-looking thing. And I know that k over x, it does this, it does this weird, thing where there's a branch in the first quadrant and the third quadrant. So that's all fun stuff. So let's talk about domain and range of these functions. So graphically, I would really encourage you to do this. When you're looking at domain, put your pencil or your hand over here and start on the left and move all the way to the right and see if the function exists the whole time. So does the function exist here? Yes. Does it exist there? Yes. Does it exist there? Yes, yes, yes. Does it exist here? Yes, it exists here. So for any x value, I can move up or down or not move at all and find a y value. So I know that the function exists from all the way over here. It's going to continue going all the way to here. So the domain of kx and linear functions is all real numbers, which I can write like that, or I can write it as negative infinity to infinity. Okay, that's great. Now the domain over here, again, I'm going to start on the left, and I'm going to move all the way to right and ask myself the question, does the function exist everywhere? Well, this is going to keep going to the left, and this is going to keep going to the right. So I think, yeah, there's no issues, there's no jumps, there's no asymptotes, there's no holes, there's no weird things. So again, the domain of this function is all real numbers or negative infinity to infinity. Again, same thing, different notation. Okay, now let's look at this graph. So it looks like this is going to keep going all the way to negative infinity. I think that the graph graph still exists over there. Okay, so I think it goes all the way to negative infinity. Then as I'm moving from the left to the right, function exists, function exists, function exists. Uh-oh, function does not exist at 0. There's no function value there, right? Here's the function, there's no function value here. So 0 cannot be a part of my domain. As soon as I get past 0, the function exists again, right? Because this is going to get really close. It's going to exist again all the way to infinity. So I can write this two ways. I can write this as negative infinity to 0 union 0 to infinity. That basically just means this or this, right? Negative infinity to 0, then 0 to infinity, but not including 0. But the way I would like to write it is just simply x does not equal 0, right? That's my preference, x does not equal 0. This is my preference, all real numbers. This is my preference, all real numbers, and that's just because it's a little bit more succinct. But this is a great way to write it as well. Okay, over here, same thing, function does not exist. I mean, does exist, but then at 0, it doesn't, and then it exists again. So we would say here for the domain, again, that it's negative infinity to 0, and then 0 to infinity, or we would simply write x cannot be 0. I like to write it that way because it's just a little bit faster. Okay? So that's the domain. So what about the range? Well, the range, we start at the bottom and go up. And you can see for both of these functions, they go all the way to the bottom and all the way up. So the range is also all real numbers. For this function, however, remember if we're looking at the orange function, the range is simply, whoops, I lost my light. The range is simply 0 and bigger. So for that one, we would just say the range is simply 0 to infinity. So the range here would be 0 to infinity, or we can write y is greater than or equal to 0. So everything from 0 up. But for the green graph, it's 0 down to negative infinity. But we always start at the bottom, so we're going to say negative infinity up to 0. So the range for the green graph here would be negative infinity to 0 bracket. We want to include 0. Or we could say y is less than or equal to 0. Now for these graphs, we start at the bottom. It looks like it goes all the way down to negative infinity. It exists, it exists, it exists, it exists. It does not exist at 0. Then it exists again after 0. Here it does not exist until we get to 0, and then it exists after 0. Right? There's no function down here. So for this one, our range would be y does not equal 0. It can equal anything else, but it can't equal 0. And over here, our range would be y is greater than 0. Or we could write 0 to infinity, not including 0. And over here, we could write negative infinity to 0, not including 0, union 0 to infinity. So a number of different ways to write these. So I just want to mention that the problem areas are these asymptotes. The asymptotes are the lines that the function approaches. They're not the function itself. They're the template within which the function operates. So yoink, yoink, these are our whoop, whoop, whoop asymptotes. And the functions are approaching those lines for very specific algebraic reasons, which we can dig into a bit more. But since there's an asymptote at x equals 0, it cannot be part of our domain. Since there's an asymptote at x equals 0, it cannot be part of our domain. Since there's an asymptote at y equals 0, and our function only exists above that, that's why we should have y is greater than 0. And since there's an asymptote at y equals 0, which is this line, right? Y equals 0, y equals 1, y equals 2, y equals 3, y equals 4, y equals 0, then that's why y equals 0 cannot be a part of our domain. So hopefully that helped thinking a little bit about notation and these graphs and thinking about how we can write domain and range. Ooh, 1450. Okay, bye.